Hello, everyone. Everyone can hear me at the moment. Hello, Suez, Thomas, who we got, Wendy, Tora. Great to have you here, and Marcel, and Lars, and Henrik, and Anders, and Alexander, and Henrietta, who's the host, and the others who I missed. Thank you so much for coming along to my talk today. I hope you can all hear me okay. If there's any technical problems along the way, I guess just dive in and get them fixed as soon as you can, and just to make sure this goes as well as possible. Welcome back to NDC Oslo. It's one of my most favorite conferences in the world. I've had such amazing times in Oslo over the last few years. Last year was a huge highlight, getting to play with Dylan Beattie and the Line Breakers on stage at the party. Some of you might have been there. It was a great time, but also being able to give my there. And it's wonderful that the conference has continued in these difficult times through to this situation. And fantastic that you've all come along and attended, and you come along to my talk today. And I'm really very, very happy that you're doing that. And I look forward to all being back together in person, hopefully this time next year in Oslo. Many of you will know my background. I am a researcher at Microsoft Research, and I am the designer of the F# programming language. And I've also worked, I guess the consistent theme in my work in the .NET and programming languages space has been to expand the role of functional programming techniques and functional programming languages to let these wonderful, powerful ideas become to spread and to become a broader application, and to help normalize them and disseminate them into broader programming experience. And I think we can see the results of that at NDC Oslo. We have talks like functional programming in C#. We have a lot of talks on like F# or functional techniques and so on. And you can see it all the way through to .NET generics and other things. These things are now spreading and becoming a totally normal part of the programming landscape. And this is a wonderful thing. But because that is my work, I tend to drill down to quite fundamental issues in programming. Things which go right to the core of how we deal with programming, right down to the programming language level. And one of those topics is the one I'm going to be talking about today. And that's about how functional programming interacts with change and adaptation, with incremental computation. And the context I'm going to be talking about it in is in the context of high-performance functional UIs. And a lot of the work I'm going to talk about today is actually based on this incredible F# initiative called the Aardvark platform. And you can find out all about Aardvark. I'll just bring up some of the web pages. Here we go. The Aardvark platform here at aardvarkians.com. You can get started, you can get touched, and you can join the research community. And these are awesome libraries for interactive, high-performance visual computing and graphics applications. And they're nearly all done in F#. There are often C# components or APIs in there as well. And you can check out who's using it, the community, the components, and so on. And I really do encourage you, if you're interested in this space, look at this, because it's really mind-blowing what they are doing there with .NET and with F#, and get involved in that initiative. So big thank you to Thomas Ortner, Georg Hase, Harald Steinlechner, and other people, other Aardvark contributors along the way, some I mentioned at the end as well. Right, okay, so what's the situation? Well, okay, there's two aspects to this situation. One is the one of sort of high-performance UI that I was talking about. There's another situation which is about this theme of functional programming expanding its range of application in ways that we didn't initially expect when we started things like F#, but we now understand just that functional programming is even more powerful than we ever thought it was, and even more applicable to a whole range of programming problems. So the world of UI is developing, and I've used this slide last year in my talk at NDC Oslo, if you were here. And the slide is between these two views on designing user interfaces. And And there are roughly two categories of user interface we're talking about, not the two I've got on the screen, but there's a high performance graphics kind of applications I was talking about just now. There are also these information rich applications, which is sort of line of business applications. And so this is about how you design the line of business applications generally. You have these MVVM components, MVVM approach over on the left, and we have this MVU approach over on the right. And MVVM is sort of the standard in the industry today. It's how the underlying components work for things like WPF and UWP and Xamarin Forms. And over on the right, you've got these new, quite trendy, quite interesting ways of doing things, which is based on this model view update. And they're very different architectures. Over on the left, you generally use object-oriented programming and you use mutable programming models. And you often do this view in something like XAML. Okay, you've probably all done this kind of work over on the right. And over on, let me just close this down. Over on the right, we have generally functional programming approaches. We have immutable models underneath quite often. And the view is often done in the same language or a mix between some markup files and sort of the view might be done in a DSL in FSharp or in another programming language such as Elm. Okay, so just to compare how information flows in these two systems. Over on the left, each of these components are mutable. So there's actual state change going on in each of them. And that it's very intrinsic to the design. It sort of influences the entire design of each of these components. You have a view here where things are changing, and you have data binding messages going back and forth to the view model. And then you have a two-way binding here between the model and the view model, when the model is perceived to be where the business logic and data is. So we're all familiar with that architecture. And the model on the right, the information flow is very different. And it's the key phrase to remember is unidirectional data flow. So if information flows really in one direction around the loop. So we start with the model. And the model is rendered by a function into the view, and the view receives some messages or generates some messages in response to user interactions or from outside events. Those get processed into an update. It generates a new model, and you re-render the view. And that's the basic information loop that's going on over on the right. So I've been through this one. And this is another view, the Elm architecture of the same thing. You'll just see these round and round unidirectional information flow diagrams in all the basic descriptions of the Elm architecture or anything involving unidirectional data flow. And just to say that this idea that we move away from objects and mutation over in the MVVM world, or at least we might have that underneath, but on top we build something that uses unidirectional data flow. This idea of unidirectional data flow in all its variations is becoming almost ubiquitous in the world of interface development. And there are quite a few different variations on this, and this is quite key to understand. People use the term MVU, generally using it for the Elm version of this, where you actually have an immutable model and you have a very pure approach to this. But if you look at systems like SwiftUI, or you look at Maui, or you look at Fabulous from FSharp, in the FSharp world, you even look at React, it has elements of this in it. And this way of doing user interface programming is becoming more or less ubiquitous. And I actually talked about these ideas last year at NDC, and these are now strongly contributing to the future of .NET UI in the context of the Maui project, which was the Maui initiative. And it's really the future of multi-platform UI in the .NET stack. For at least it's Microsoft's sort of big new initiative in this area. And you can see from the blog post about Maui that they are enabling developers to write fluent C#, and you will be able to do it in F# as well, to UI to implement the model view MVU pattern or a variation on that pattern. And it uses one-way flow of data and state management and a code-first development experience. Those are the key parts of MVU. Right, so that's the situation. But the question I want to ask really is functional relevant to high performance UI? Because there are key trade-offs in this MVU approach. And what do we mean by high performance UI? And this is actually an application that is using the techniques, the functional adaptive data techniques I'll be talking about today to do high performance functional UI. And it's a visualizer. It's one of those wonderful applications of coding for it's all to do with the reconstructing the Martian surface images based on the data that's coming from the rovers on the planet. And you can find out a lot more about this application in this wonderful talk, which I will link at the end of the talk. I almost canceled my talk and just decided to play Thomas Ortner's talk from GPU Day 2019, The Future of Computing, Graphics, and Data Analysis. And in this talk, Thomas gives a wonderful overview. Let me just maximize this. A wonderful overview of how he's using these techniques for functional programming for high performance data and UI. Now, let me just skip through some of this. And you can see some of the applications they're using there. And one of the key things in this area is they're reaching for functional programming for those classical reasons that you want to reduce your time to market and you want to be able to crank out high quality prototypes on a low budget. So they're looking for that productivity of functional programming in this extremely complex and technically challenging domain. Okay, so that's our context here, and that's the video talk you can go and watch. Okay, so let's go back to basics. Now we've set the context for where the areas in which we're trying to apply functional programming. We want it in those information-rich apps, but we want extreme versions of those where you have incredible amounts of information in the application and you have high rates of change in the application. Okay, so just to get back to basics, here's a typical structure of an MVU app. We have the model from which a view is generated up here. We have the messages which cause updates to the model. We have the initial state for the model, the initial model. And we have the logic which updates the model. And that's in a sense all the business logic. And part of the wonder of MVU is that you get to unit test these parts of your code separately. You can test all your business logic through this and this is all straight up pure functional programming. There may be some interaction with some components on the outside, some database components and the like, some connection handles. They will typically be stored in the model as well. Okay, and then you have the key thing, which is the computation to construct the view. And here we have, say, so if you're doing this, then generate a label, otherwise generate a button and so on. And in more detail, depending on the DSL you're using to express your view, it will look like this. We have model, we have messages, is the button pressed or not, the initial model. If the button is not pressed, we update the model, and then we have the view, the view, which is a dynamic view. It depends on whether the model is pressed. So the entire view will change. The entire DOM tree that we have ultimately will have to change based on that button press, and the entire view gets brought down, and an entire different view might get brought up as each message is processed. And the beauty about this, as we said, is it's all just functional programming. The UI becomes calculation. And the wonderful thing, when you think of functional programming, it's not all these abstract ideas and everything. It's actually really something we do all the way through school as we write down calculation after calculation. It's algebra. It's just information and calculation rather than state and mutation. And so the whole UI just becomes this calculation. And because the information flow is unidirectional, then you can always track down where information is being lost, where it's being gained, where bugs are being introduced, and you can break it apart. Each bit you can break apart and unit test separately. And the views are recomputed, and then a shadow DOM is produced. It does a diff between the shadow and the actual DOM and applies some changes to the actual DOM. Okay, that's beautiful. But, well, we've got an issue here, and this is really at the heart of what I've really been getting towards, because are you serious that we are going to use functional programming for rapid update, data-intense interactive UI. And you look at that and you just say, you can't possibly be serious that this approach, which we've just talked about, is going to be suitable for high performance UI, because you're recalculating the view as you, even if you are recalculating a shadow view, then, and doing a diff, you still have to do that diffing process. It's still computationally intensive in a sense on each update to work out what needs to change. It's very declarative, but working out the incremental version of that, it's hard. But what if we change a question so the cat, we see our cat and we think, and the question is, what if we're doing incremental functional programming for rapid update, data-intense, incremental interactive UI? Okay, so if we insert that keyword incremental, then we begin to consider that perhaps we are talking. So incremental and functional, what even is that? And that is really at the heart of the talk today. I've set the scene and I've got the question. What is incremental and functional when it really comes down to it? And just stop and think to yourself. Take a moment to stop and think, what word associations, if someone comes along to you, or a customer comes along to you and says, hey, we need an incremental XYZ. We need to, process new information as it comes in and changes. And you might be, if you're functionally trained, you might be thinking event sourcing, and that's good. That's very related to the techniques I'm thinking about today. But if you're object-oriented trained, you will immediately be starting to think about, okay, I'm going to have objects, I'm going to have mutable state, I'm going to be making incremental updates, I'm going to be writing lots of code to maintain that incremental state along the way. And so if you do, you might also be thinking about, okay, we're going to have a dependency graph. We're going to be doing asynchronous update to that dependency graph. We're probably going to get ourselves into all sorts of concurrency problems and so on. And that's, for me, it's interesting to do. I went and I made a word graph to myself, copied out some words and made this nice graphic, entirely not based on any information, except what's in my head about what it makes me think when I hear the word incremental. I think update nodes, dependency graphs, async commutation, probably a static graph. If I suddenly think, oh my God, it's going to be a dynamic graph and incrementation, this is going to blow my mind. Okay, so it is a complex space that challenge people. And I've got a little secret for the functional programmers as you sit around your team and think, where are the mutable objects, and where is the kind of static thinking? Where is the kind of object orientation in the worst? Many good aspects of object programming, but if you think about object orientation kind of thinking coming in, then one of the likely sources of immutable object thinking in your team is going to be to do with incremental processing of results. Okay, and so part of what I want to get through is not just the situation, but if you as a functional programmer can master incremental functional programming, you will be able to do more functional everywhere and build better systems with better reliability at lower cost. And and one area you should learn is absolutely event sourcing. And as I said, it's related to what I'm talking about today. And this library on the UI side, or this set of techniques, is a similar core thing you can learn. It's like having a tool in your tool belt to go and tackle many different problems in the future. Okay, so let's just recap where we are using some slides from the wonderful Yaron Minsky. Your UI as an incremental computation. So this is the traditional model of VDOM gets applied to the DOM in the view function. And traditionally in these MVU systems, you compare, as the model changes, you compare the VDOMs that are produced, you rerun and generate the view function, and then you get a diff and you apply it to the actual DOM. And we all know that's what React does, and that's what many of these systems do. And but we are going, but look at this. We're recomputing this function down below here. We are recomputing the VDOM on each stage. And yeah, you recompute the VDOM. This is the same question we asked before, but drilling down to the more specific, you can't be serious. You incrementally recompute the VDOM. Now we are talking. Okay, so we want to say if there is a diff to the model, so we want this to not be a whole new model, but we want to know what this actual diff is. Then we compute a diff to the VDOM, and we run all the way through. And this kind of says, well, we're not just going to be doing MVU, which is functional model, functional view, functional update. And this is what Elm, Fabulous, and Elmish and others do. We actually want a variation on it, which I'll call sort of delta MVU, which is a delta to the model, a delta to the view, a delta gets propagated through the update, and a delta to the view. Okay, so to get down to the question, we're asking incremental plus functional, what even is that? One place you can go, and there are actually many actual technologies which fit in this particular intersection in software design. And this is not the be-all, it's an end-all of it, but one place you can go to learn about it is FSharp.Data.Adaptive. And I really like this library, and that's why I'm drilling into it in this talk, because it exactly captures this intersection between functional and incremental for the working .NET programmer. You can use this library from C# as well. It has a design API designed for use from C#, and that is great. Appropriate set of extension methods and the like. And please, you know, try out this library, contribute to it. It's just coming up to version 1.0. It's a very high quality library. I've been using it, and it's extremely well tested based on code from the Advarkians, who I mentioned before. And it really, what I like is that it's not tied into any other UI framework or anything. It's used by those things, but it's just conceptually independent, and you get to learn the intersection of techniques. And I think it's one of those things, actually digging into the code, if you're an F# programmer, is actually a really interesting experience as well, because you learn something from that. You learn a set of new techniques. Okay, so let's look at how this works. And remember, the key thing is we want the FSharp.Data programming model, as in like FSharp.collections of lists, and you could be called FSharp.collections.adaptive, actually, rather than FSharp.Data.Adaptive. So we have these collections like FSharp lists. We know as F# programmers, you take a list and you map it and you get a new list. You can filter that list. You can sum that list. We have all this wonderful set of operators you can use to take functional data and transform and shape and reduce it out. And that programming model is consistent for lists. It's consistent for arrays. It's consistent for sequences and for sets and for maps and so on. And these collections all support the same set of operations. And having done some C# programming recently, I mean, I know there's C# link, but the F# functional collection programming model is actually really nice and really consistent across all these different types. So it's something that all F# programmers absolutely know and love. So that's that model, and given you know that model, you want a really simple step towards the incrementalization of that model. And that is, we're going to have an adaptive list, which you can map, and we're going to have an adaptive filter, and we're going to have an adaptive sum. It's the same programming model, you just sort of put A on the front. And internally, instead of having a list of data, you have the propagations of delta, of changes to that list. And you can, as you have your own functional collections, and your own functional data types, your own models and the like, you can actually write the same, you can implement your own adaptive version of this programming model. Okay, so continuing on, let's just walk through some basics of how this actually works in practice. I'm going to do that in Visual Studio Code, and I am going to just, so I have Ironide installed in Visual Studio Code. I'm using FSharp.Net Core programming down below, FSharp Interactive. And here is some functional programming. So let's just do the usual, let's just create a list of 10,000 elements here. And we're going to multiply each element of the list to generate a new list like this. And we have a new list, whether it's multiplied by 10, 10, 20, 30. Okay, so it's the usual information and calculation here. And we have, except I'm actually going to put a print down below so you can see 10,000 prints coming out there. Okay, and we have that, and we have some information. We'll do a transformation on that information to multiply it up by 10 again. So we have our 2 steps in the pipeline, and then we will sum that result up, except, what did I do wrong here? Okay, I'll drop this down to 1,000. Okay, we have the result down there. Okay. Now we can wrap those steps of that pipeline up, and we can take the input list here coming in, and we can have a function that computes those results. A function taking an integer list and reducing it down to an integer, and we compute the results here. Actually, I was going to drop this down to 10,000 here. And I'll do it again, dropping it down to 1,000. Okay, so now what if the result is actually, what if this list actually changes? That's the kind of thing we want to get down to, is what if your input actually has one less element in it? Say the element 5 is removed. So we have the list from this up to 1,000 here, and we'll put that in brackets here. We'll get rid of this filter here, and that's now our input, and we get a different result coming out. As you can expect, it's reduced. But you'll notice that we're recomputing all the work every time. We had one item removed from that list, and there was an incremental change where 5 disappeared. And you think to yourself, how would I adapt that? How would I avoid doing that work all over again? Okay, that is a key problem. It's like suddenly programming has become hard, right? Or from what looks like so trivial, we're just multiplying by 10 and multiplying by 10 and adding things up, and suddenly I don't want to do all that work again in response to that change of that removal of 5. And you think to yourself, oh my God, this is going to be really quite tricky. All that state I'm going to have to maintain in order to make sure I don't redo that work. Okay, so now let's do this in the adaptive version of that. So we have an adaptive input. So this is the initial state of the initial input into our adaptation. And we were using list up above. I'm going to use a set here. And we do a map, and we do a map over that adaptive set, and we're doing an adaptive sum. So we've started off with our input, and we're doing our adaptation, and it's effectively functional programming or functional transformation. And we observe the result at the end. Actually, I was going to change this down to 1,000 here. Just let that run through. And it will have the same problem we had before. And we'll do that sum, and we'll take a look at the result. And the result is, sure enough, it's correct. But now something changes. A change comes into the system, and changes are still ultimately at the fringes of the system. You still have a change being made imperatively. And then you have this functional flow all the way through, and then you have a change being observed. Okay, so you still have an imperative changes at the edges of the system, but the core of your code is still a functional transformation. And we had removing the element, and now we do the force here. You'll notice the result has come back, and absolutely nothing has been recomputed. Okay, now let's try that again and say, what the heck happened? Okay, so let's add a new input. I'd add the input 20,000 into the set of results, and we reobserve. Wow. So all that work that we did to compute the first result up here, which did all those printing out of 10,000 things, all of that, all of that got saved somehow. Okay, in whatever data flow is going on, however things are being computed, and you can look up the details in FSharp.Data.Adaptive about how this works. All of that got recorded and saved, and all those intermediate tables to work out what to do and what not to do. When we removed the result, it just said, what did it do? It said, okay, so this result, and it had recorded how that 5 had gone through this mapping and given us 500. And it just said sum. I have to change a sum result in response to a change for what's coming in. Well, I just subtracted off. Okay, so I did the subtraction there. Then when we did the addition, well, it multiplied that up. It actually did do those steps. You can see those steps being done. A new element comes in. It says, I've got a new element and we're doing a map. Okay, I'll work that out. And then we get to the sum and it's a new element in the sum. So I'll just add it on. Okay, so it's incrementalized the entire functional declarative computation. It has built up an incremental version of that can respond to add and remove events. Okay, so that's the core idea of, let me switch across to FSharp.Data.Adaptive. And here is the library, FSharp.Data.Adaptive and adaptive values. And it'll run you through that. It'll run you through how to build a little Excel spreadsheet, which sort of does incremental update and computation, or things that are like a code version of an Excel spreadsheet. And you can look at how you can build up these graphs of what feel like graphs of adaptive computation. Now, crucially, these graphs can also have dynamic dependencies. They don't have to be merely static. And we can talk about that in just a moment. So just say FSharp.Data.Adaptive, your data as incremental computation. Okay, so over on the left, you have your usual F# immutable data. And over on the right, I've given the corresponding thing for your adaptive version of your data. So where you have an integer, you'll have an adaptive value of an integer. And over on the left, you have a list, you have an adaptive list, a set, you have an adaptive set, a map, you have an adaptive map. And if you have an actual list of values, you'll write a list 1, 2, 3 on the right. If you have a computation, so for instance, you're treating time as an adaptive value, they're 1.0 plus now.seconds, you'll write a val and you'll get the current time using the F# workflow syntax, let bang t equals now, and you will take t.seconds and add it 1 and use a return. And over on the right, you've seen the pipeline just like we just had. Over on the left, sorry, you have list.map, filter and sum, you have a list map, filter and sum. Okay, so you can see how you can take functional F# functional code and do a fairly straightforward translation over on the right until you have your adaptive version of your code. Okay, but we're talking user interfaces, and you say, oh, this is all just lists and sums, lists and maps and sets and things, okay? And so what about the user interface? Okay, well, let's just talk about the DOM. Okay, so because ultimately we're going to have to compute a view in the MVU programming model. So what is the DOM as data? And this is a typical F# programming model for the DOM as data. Each DOM node has an ID. It has a set of attributes. It's a functional map from strings to some kind of attribute value. And it has a set of children. And that is a tree of data that is a full declaration in F# for a typical DOM, a DOM tree. Nice and simple, recursive structure. Okay, so what is the DOM as adaptive data? And this is a kind of thing you have to learn when using this library. When you have some data structure, you say, so you prototype out your code in terms of beautiful, pure functional programming. And then you say, I want to incrementalize that. And you say, where are the key points where you need to insert your incrementalization? And those usually come down to the insertion of this magical A letter, A for adaptive, at exactly the right places. So in the DOM node, you now have each DOM has an adaptive map of attributes. What does that mean? That means your DOM node, its attributes could change over time, okay? There will be these deltas of changes to these maps, additions of attributes, changes of attributes, removals of attributes, flowing up through your DOM node. Okay, so it becomes an adaptive map. Every single DOM node now has an adaptive map. So as you have your view, each thing, you getting the perspective of where your DOM node can change. Your children of your DOM node is now an adaptive list of children. Okay, so what does that mean? You can have new children, it can have removed children. It can change over time. And don't forget, they themselves, it's a recursive structure going all the way down. You have adaptation all the way down, all the way down. Your stack of turtles can change anywhere along the way. Okay, so here we have in a 4-line declaration, we have a declaration of one of the most difficult to implement programming language structures, a tree that adapts and changes over time, and where there's a coherent notion of what are the deltas to that tree. Okay, so you now have an adaptive DOM. That simple. Now there is complexity here, but in terms of the user underneath, absolutely, and maintain in this thing is the way the adaptive maps are implemented and maintained is absolutely key, which is why it's in this wonderful library called FSharp.Data.Adaptive. This is a recursive adaptive type. The whole shape of the tree might change and adapt. Okay. So when you have an adaptive DOM, that is the key. Those 4-line data structure you see there is the absolute magic that's sitting inside a high-performance functional web UI. Okay, and just to say that it's not just about the DOM. The MVU programming model tends to focus on the DOM, but actually, if you have adaptive scene graphs, then you'll have high-performance functional graphics UIs. And that's what's covered in the Aardvark platform. It's essentially the key idea that at the core of a lot of what Aardvark is doing is you have this adaptive scene graph. And you can go and look at Aardvark. Okay, right. Just to say, okay, let's say we have the adaptive DOM on the left, and I haven't really represented the change that's happening to that thing and the deltas that are happening, but I've talked about it. Children get added, children get removed. Attributes change, the whole shape of the tree can kind of change as things go on. Now, and it's not a static graph, okay? It's absolutely a dynamic thing. So you do full-on dynamic UI with this. Now, the actual code that's in these frameworks that sort of consumes these changes, ultimately you have to, in some sense, listen to the changes coming from one of these adaptive collections or one of these adaptive data structures. And ultimately you have to make changes to the real DOM. Now you don't have to do this as a user of this thing, but if you're going to work with FSharp.Data.Adaptive, you might, and build interesting new data structures, you might have to write this kind of code that listens to changes on an adaptive thing and makes changes to an actual thing. And it's actually interesting exercise and puzzle, and once you solve it, you encapsulate that listener, and it just becomes a simple combinator which says sort of propagate changes from here to here. And you have this sort of corresponding set of listeners which sort of listen in to the changes coming over from the left and make corresponding actual mutations, actual changes over on the right. And there are samples in FSharp.Data.Adaptive. There's some pull requests giving those samples as well, listening in at the edges. Okay, so what have we gained by moving to adaptive functional data? You get very, very minimal recomputation and update. You already saw that minimal recomputation for that sum. That corresponds through the entire UI programming as well. Adaptive data can have dynamic shape and dependencies. You're not being tied into this static thinking, but it can have this sort of static outer part for performance. That is, you can make sure you're not there is a risk here that you end up recreating the entire adaptive part in response to just one little change anywhere in the graph, and you have to be aware of some techniques for avoiding that. So you have this sort of static outer part. And also there's this thing that these adaptive data is recomputed on demand, okay? And that is actually critical, and especially in the context of these adaptive scene graphs, because of course you only have one in your typical game or visualizer of the kinds we've been seeing earlier on. You only have one part of the Martian surface that you're looking at, even though you've actually got this huge information space available. And you want to only compute that part on demand. As things change through your user interface, or as the camera changes through your views. Okay, and just how does it actually look in code in a typical Delta MVU app, an incrementalized MVU? Then you have a model, you have an update, stay the same. You have this interesting bit of code automatically synthesized, which generates from your functional model, this tool called Adaptify. It's part of the FSharp.Data.Adaptive sort of tool chain, gives you an adaptive model. So where your individual adaptive values, like is the button pressed, goes from being purely functional to an adaptive functional, and it gives you a thing which diffs out the models to compare those two models. So these parts actually stay purely functional, but it's only the view which is written with respect to the adaptive model. So you still get to do all the nice functional programming, but the delta, you get the deltas on the views. And the view now becomes a thing which is built on the adaptive model and sort of listens to changes to that adaptive model. And in this case, it's an adaptive value, which when the model is pressed, then you'll get a change in the appropriate view. And yeah, this is a typical way that you'll see in things like the adaptive Elmish MVU programming models. This is the kind of code you will be typically seeing, the adaptive view. Okay, so I am actually close to finished. I will be finished well ahead of time. The summary of the whole talk is really that MVU is a beautiful programming model. You see it starting to influence, in Swift UI, you see it in Maui UI, and you see it in Elm initially. It's absolutely amazing for information-rich apps, but it does have performance issues for high performance UI and extremely data-rich UI. And so you're beginning to see these variations on MVU, which allow adaptive functional data to make this MVU point of view, this functional point of view, relevant to amazing high performance UI. And just some of the examples that have been done with the Aardvark platform. I've mentioned the robotics viewer on the right. You mentioned this high quality lighting simulation over scene graphs. This is some of the best visualization research. I mean, there's a lot going on in these kind of areas, but it's just, they're cranking out these incredibly incredible applications with high productivity over extremely complex data sets based on what they're doing in the Aardvark platform. So, and the other part, that's the high-level conceptual thing that you'll see repeated in many different settings over the next 10 or 20 years, is this thing about adaptive functional data making it relevant. But if you want to actually use adaptive functional data today, there are several different options floating around the .NET space. Some of the toolchain, some of the MVU systems like Maui have things actually incorporated. Some of these elements actually sort of incorporated into Maui itself. But if you want to actually use the general notion of functional adaptive data today, you can do that with FSharp.Data.Adaptive and get involved and contribute to that library as well, and build things on top of it. It really is an amazing bit of technology. Some resources for you. There's 3 talks from the Aardvarkians. Georg Haase, Functional Adventures on High Performance Computer Graphics. We have the Thomas Ortner talk, which I mentioned before, Functional Programming Boosting Scientific and Industrial Research. And this one from Harold Steinlechner and Georg Haase, on functional programming versus efficiency. A lot of these things about incrementality we talk about, and also other ways to get super high performance using your functional programming language. And there's an entire course on this from one of the Austrian universities. And we have the repos here, the Aardvark platform and FSharp.Data.Adaptive.